In this video tutorial, we are going to learn how to insert and configure the industry standard Alligator Technologies USB PGF-S1 programmable instrumentation amplifier with a variable frequency low-pass filter into a sensor signal sampling system. I'm going to assume you are interested in attaching any kind of sensor or microphone to an ADC or analog to digital converter. A typical question is, why do I need a low-pass filter when I can connect the sensor directly to the ADC? I'm going to greatly simplify an answer to that question. Nyquist theory dictates that a digitally sampled signal must be bandwidth limited before it is acquired. Yes, you can connect your sensor directly to an ADC, but the result will include extra junk that may represent as alias or ghost signals that can move around the frequency band in odd directions. Excessive noise, and worse, it is impossible to remove these artifacts with digital post-processing. Now let's dive in deeper and look at the detailed operation of a low-pass filter and how to configure it perfectly to create clean and accurate results. Low-pass filters operate on a raw signal to allow frequencies below a cutoff to pass through at full amplitude and to reduce the amplitude of raw signal frequencies above the cutoff. The word cutoff is a bit of a misnomer because in electronic implementations of low-pass filters, it neither cuts off nor is it the actual starting point of attenuation. That's why Alligator Technologies prefers to call it the corner frequency. Here is a graph of a typical low-pass filter frequency response. The y-axis is the amplitude measured in decibels. A decibel is the inverse logarithmic representation of output to input voltage. The x-axis is frequency from 0 Hz, or DC, to the maximum bandwidth of the filter. The corner frequency is defined as the -3 dB attenuation of the input signal. The -3 dB corner frequency marks the end of the filter's passband. It also marks the start of the filter's attenuation band. The end of the attenuation band is the point at which the electrical output becomes immeasurable by the ADC. This point is also the start of the rejection band, which stretches out to infinite frequency. There are two limitations to analog to digital converters. The first is the sampling rate, and the second is the smallest resolvable voltage. Both of these limitations play a factor in defining the optimal setting of the low-pass filter's corner frequency. Going back to Nyquist theory, the Nyquist frequency is the highest frequency allowable when referring to bandwidth limiting the input signal. The Nyquist frequency is exactly 1/2 of the sampling rate. So, if an ADC sampling rate is set at 10,000 Hz, then its Nyquist frequency is 5,000 Hz. The other limitation is the smallest resolvable voltage. In terms of dB, a 16-bit resolution ADC has a resolvable floor of -96 dB. The optimal setting for a low-pass filter corner frequency is positioned so that the end of the attenuation band is at the junction of the ADC's lowest resolvable amplitude and the Nyquist frequency. A common mistake is to set the corner frequency at the Nyquist, allowing resolvable although attenuated frequencies to be sampled erroneously by the ADC, unless, of course, one is aware of the consequences and prepared to differentiate between the real signal and the potentially resulting artifacts. Now let's move beyond theory and actually connect and configure a low-pass filter to a digital sampling system and measure some real signals. In this demonstration, we will be using a function generator to simulate the electrical signal from a sensor transducer. When testing the integrity of a sampling system, a function generator is a very useful tool for creating a known quantifiable signal. It's really quite simple to connect the USB PGF-S1 into the sampling system. Connect the sensor to the input and connect the ADC to the output. Plug in the USB for the host computer control and then apply power. For demonstration purposes, we are going to set the corner frequency of the filter to 5,000 Hz. Here, a pure tone with a sweep from 100 Hz to 12,000 Hz is applied to the input. On the oscilloscope screen, the input signal to the filter is pictured in blue, and the output signal is pictured in white. As the input signal is swept through the 5,000 Hz corner frequency, you can clearly see the output signal attenuates down to nearly 0 volts. Changing the input signal to plus or minus 10 volt white noise, observe that at the output, the noise is very nearly removed. Passing through are frequencies below the rejection band, causing a slight bit of wiggle in the output signal. Combine a fixed frequency tone with the white noise and look at the output. The pure tone has been extracted from the noise. Now I'm going to show you where the Alligator Technologies filter really shines. Extracting a small signal from a field of noise. To start, let's increase the amplifier gain to its maximum 10,000 level and apply a plus and minus 1 millivolt sine wave embedded in 2 millivolts of noise. Look at how small the input signal is. At the output is a nice, clean, plus and minus 10 volt sine wave. This is truly outstanding. The Alligator Technologies USB PGF-S1 is extremely affordable and an invaluable tool for accurate and clean signal digitizing.